Did you know the iconic Brooklyn Bridge has remained standing for well over 100 years, supported by nearly 14,000 meters of steel cable? That raises an important question. What exactly happens during manufacturing that gives these slender strands the strength to hold up structures of that magnitude? To produce a cable tough enough for critical, high-risk applications, the process begins far from any city skyline, deep inside iron ore mines, and continues through the intense environment of a modern steel mill. There, carefully engineered alloys are liquefied at extreme temperatures, poured into solid billets, and put through strict quality checks. Only after passing inspection are they stretched into fine wires and precisely twisted into finished cables, ready to be installed in projects across the globe. In this video, we're breaking down that entire journey, from raw material to final product, exploring the heavy machinery, the technical precision, and the complex operations that transform what appears to be simple twisted metal into a material capable of surviving decades in some of the harshest conditions on Earth. Steel wire rope first emerged in the 1830s in the coal mines of Germany. At the time, traditional hemp ropes were failing under increasing loads. Replacing them with steel allowed mine hoists to travel hundreds of meters underground with far greater safety, paving the way for large-scale industrial extraction. Fast forward nearly 200 years, and steel cable has become essential across countless industries. Today, global demand exceeds 10 million tons annually, spanning infrastructure projects, heavy manufacturing, oil and gas operations, maritime transport, and even renewable energy systems. Elevators in skyscrapers worldwide depend on steel cables, making it possible for modern cities to build higher and reshape their skylines. What makes this material truly remarkable is the relationship between its relatively small diameter and its staggering load-bearing capability. Dozens of high-tensile steel wires are tightly wound together, creating a structure that balances flexibility with strength. The helical pattern distributes stress evenly throughout the cross-section, preventing concentrated weak points. The result? A cable only a few inches thick can carry loads measured in hundreds of tons, an engineering achievement that defines modern industry. And it all begins deep underground, in vast iron ore mines where the raw ingredients of strength are first extracted from solid rock. The process begins with powerful drilling rigs punching deep into solid bedrock, carving out precisely placed holes for explosives. Once everything is set, carefully controlled detonations shatter the rock face, breaking it apart and exposing rich deposits of reddish-brown iron ore. From there, massive hydraulic excavators move in. These machines scoop up chunks of ore weighing dozens of tons at a time and load them into haul trucks built to carry hundreds of tons per trip. The trucks operate almost non-stop, traveling along designated haul roads to transport the material out of the open pit. At the processing yard, the ore is dumped into large feed hoppers and directed onto conveyor systems that can stretch the length of several football fields. Along the way, vibrating screens sort the material by size while powerful magnetic separators extract unwanted debris. Dirt, sand, and other coarse impurities are removed before the ore moves any further. To prepare it for the next stage, the material is often crushed into smaller fragments. Reducing the size makes transportation more efficient and improves performance during smelting. From there, heavy-duty railcars and bulk cargo vessels take control, each capable of moving thousands of tons in a single shipment. This continuous cycle of mining, sorting, crushing, and transport operates around the clock, ensuring steel producers receive a constant, reliable flow of raw material, the foundation for high-strength cable manufacturing. Once the trains arrive at the steel plant, the transformation intensifies. Iron ore is blended with recycled scrap steel and charged into a towering electric arc furnace, a structure comparable in height to a multi-story building. Inside, enormous graphite electrodes unleash massive electrical currents, generating temperatures above 2,900 degrees Fahrenheit, hot enough to liquefy solid metal into a churning, glowing pool that resembles molten lava. At this stage, chemistry becomes critical. Metallurgical engineers introduce carefully measured elements to fine-tune the steel's performance. Manganese is added to boost strength, chromium or nickel improves corrosion resistance, and silicon enhances flexibility and ductility. Every addition is calculated with precision, shaping the molten metal into a material engineered for extreme mechanical demands. At this stage, flux materials such as quicklime and fluorspar are added to the furnace. These compounds react with unwanted elements and create a molten layer known as slag. Floating to the top like a protective blanket, the slag works as a natural purification system, trapping impurities and separating them from the liquid steel beneath. As a result, the metal becomes significantly cleaner and structurally stronger. Inside the furnace, powerful electrodes continue to generate intense heat while simultaneously stirring the molten mixture. Advanced digital sensors constantly analyze the chemical composition in real time, making microscopic adjustments to maintain exact specifications. Every batch must meet strict metallurgical standards before it can move forward. Once the steel reaches the required purity and precise chemical balance, it advances to the casting phase. Modern steel plants no longer rely on outdated batch pouring methods. Instead, they use continuous casting systems. The glowing liquid steel flows steadily into water-cooled copper molds designed for rapid heat extraction. The moment the molten metal contacts the chilled mold walls, a solid outer shell forms almost instantly, while the interior remains liquid. Gradually, solidification progresses inward from the surface toward the core. By the time the strand exits the mold, it has formed into long, solid billets, often several meters in length, typically shaped with square or rectangular cross-sections. These billets are still extremely hot, reaching temperatures in the thousands of degrees. Rather than allowing that heat to dissipate, they are transferred immediately to the primary rolling mill to take full advantage of the retained thermal energy. Inside the rolling mill, enormous alloy steel rollers, some measuring several meters in diameter, rotate with tremendous force. As each billet passes between them, it is compressed and stretched. With every pass, the material becomes thinner and longer, gradually reshaped under immense pressure. The steel moves through a sequence of rolling stands, each one refining its dimensions further. Step by step, the once blocky billet transforms into intermediate forms such as round bars, flat strips, or elongated slabs, preparing it for the next stage of processing. Because the steel remains at high temperature, it stays ductile enough to deform without fracturing. Meanwhile, the repeated compression reorganizes its internal grain structure. The metallic crystals become more aligned and consistent, enhancing uniformity, increasing strength, and improving long-term structural stability. This controlled reshaping at extreme heat is what turns a raw cast billet into engineered material ready for precision wire production. Before the material can become cable, it must first be transformed into precision wire. After hot rolling shapes the steel into intermediate forms, it moves to the cold processing line, where accuracy becomes the top priority. The first step is rapid cooling. High-pressure water jets spray the red-hot bars, bringing their temperature down under carefully controlled conditions. Once cooled, the steel enters another sequence of rolling stands. Each station is equipped with hardened alloy rollers that compress the material with tremendous force. Pass after pass, the bar becomes thinner and longer, its dimensions gradually refined. Whether the original shape was square or rectangular, it is steadily reduced and reshaped into round or flat profiles specifically engineered for the next phase, wire drawing. That's where the real precision begins. In the drawing stage, the steel is pulled through a series of hardened dies, each one slightly smaller than the last. With every pass, the diameter decreases, the surface becomes smoother, and the internal grain structure grows more compact and consistent. Unlike hot rolling, this process takes place at room temperature. That makes control absolutely critical. Engineers must carefully regulate pulling tension, drawing speed, and the friction between the wire and the die. Even a minor imbalance can cause snapping, dimensional variation, or loss of the flexibility required for future twisting. Modern facilities rely on laser measurement systems positioned along the production line. These sensors continuously scan the wire's diameter with microscopic precision. If any deviation is detected, automated control systems instantly adjust the pulling force to maintain exact specifications. The outcome is tightly wound coils of high-strength steel wire, manufactured with near-perfect dimensional accuracy, material engineered specifically to meet the demanding standards of cable production. Achieving the correct diameter is only part of the process. To meet demanding mechanical performance standards, the wire must go through one of its most critical stages, heat treatment. At this point, the steel wire is fed into a high-temperature furnace, where it is heated to roughly 1,500 to 1,700 degrees Fahrenheit. Inside, the environment is carefully regulated. Engineers control the gas mixture and heating rate with precision to prevent contamination and ensure consistent results. As the temperature rises, the wire begins to glow red. But the real transformation happens on a microscopic level. The intense heat restructures the internal crystal lattice of the steel, reorganizing the metallic grains. This controlled alteration creates the perfect balance, hardness for supporting heavy loads, combined with enough ductility to allow bending and twisting without fracture. The moment the target temperature is achieved, timing becomes critical. The wire exits the furnace and immediately enters the quenching phase. Powerful streams of high-pressure air or specially formulated industrial oils cool the metal rapidly. This sudden drop in temperature locks in the newly formed internal structure, preserving the mechanical properties developed during heating. Once heat treatment is complete, the wire moves directly into another vital stage, corrosion protection. Depending on its final application, each strand receives a protective coating. The most common option is zinc galvanizing, though some cables require advanced polymer coatings for specialized environments. In settings exposed to rain, humidity, saltwater, or chemical vapors, this protective layer serves as an invisible barrier, shielding the steel from oxidation and long-term degradation. Before any coating is applied, the wire undergoes thorough surface preparation. It is cleaned in a controlled acid bath to remove grease, debris, and even microscopic traces of rust. A perfectly clean surface is essential for proper adhesion. After cleaning, the wire is either submerged in molten zinc for galvanization or routed through a polymer coating system where temperature, pressure, and application thickness are tightly managed. Uniformity is non-negotiable. The coating must bond securely and remain free of voids or air pockets. Even a tiny imperfection can become a starting point for corrosion, eventually compromising the entire cable in real-world conditions. This combination of thermal refinement and protective shielding ensures the wire is not only strong, but built to endure. Even with its corrosion-resistant coating in place, the wire still isn't ready for real-world duty. One final and uncompromising phase stands in the way: inspection. This is where every microscopic imperfection is exposed. Using high-precision sensors and automated scanning systems, the wire is examined from end to end. Its diameter must remain consistent within fractions of a millimeter. The surface is checked for distortions, warping, or subtle geometric irregularities. Even the smallest variation, if ignored, could eventually lead to structural failure under heavy load. Every measurement is digitally recorded, processed, and compared against strict engineering specifications. The moment a deviation appears outside acceptable limits, that wire is automatically rejected and removed from production. This isn't just routine quality control. It's a rigorous filtration system, ensuring that only the most uniform, structurally sound wires move forward to the next stage of transformation. Once approved, the individual wires advance to the stranding line, where they are assembled into a finished cable. Here, dozens, sometimes even hundreds, of wire spools are mounted onto large rotating frames. As the machinery comes to life, the frames spin in synchronized motion around a central axis. Each wire is pulled under carefully controlled tension and twisted together into a precisely engineered helical configuration. Before this process begins, engineers determine the core design. In high-load applications, a steel core is selected to maximize tensile strength and overall load capacity. For specialized environments where weight reduction or corrosion resistance is critical, synthetic cores such as polypropylene may be used instead. The choice of core directly influences the cable's final performance, whether it will support extreme structural loads or operate in environments where durability and flexibility are equally important. The process begins by organizing individual wires into smaller sub-bundles known as strands. These strands are then helically wrapped around the selected core, gradually forming the complete cable structure. Throughout this operation, precision is everything. Integrated sensors constantly track tension levels, twist angles, and vibration patterns. If a single wire is stretched too tightly or allowed too much slack, automated control systems instantly correct the imbalance to maintain perfect alignment. Speed is equally critical. Rotating too quickly can distort the wire geometry, while operating too slowly reduces production efficiency. Every movement is calibrated to achieve structural accuracy without compromising output. Once the initial layer is formed, the machine proceeds to build additional layers, winding them tightly and systematically according to a predefined engineering blueprint. Each layer plays a specific role in the cable's performance. The outer layer is engineered to resist abrasion and surface wear. The middle layers carry the majority of the tensile load. The inner layer provides core stability, maintaining the cable's overall shape and balance. This strategic distribution of forces is what allows the finished cable to remain flexible enough for installation while still capable of supporting loads that can reach hundreds of tons in real-world applications. But even at this stage, the cable isn't fully prepared for service. Before deployment, it must receive a final protective treatment, lubrication. Depending on the cable's intended environment and structural design, lubricant is applied either by full immersion or through a high-pressure spray system. The feed rate of the cable is synchronized precisely with the spray mechanism to ensure consistent coverage along every inch of its length. Flow meters and temperature sensors regulate the lubricant's viscosity and volume in real time, guaranteeing uniform penetration. The oils used are typically mineral-based or synthetic formulations, engineered to seep deep into the microscopic gaps between twisted wires. For cables destined for marine conditions or applications involving constant motion and dynamic stress, the lubricant is fortified with specialized additives. These enhancements improve resistance to oxidation and guard against electrochemical corrosion. This final stage is essential. It preserves internal flexibility, reduces friction between strands, and ensures the cable maintains its mechanical integrity long after leaving the factory floor. Even after lubrication, the cable still has one final challenge to face. Before it can be trusted in the real world, it must prove its strength under extreme testing conditions. To ensure absolute reliability, the finished cable is subjected to a series of demanding evaluations. Massive hydraulic tensile testing machines grip the cable and apply increasing force, pulling it harder and harder until it ultimately snaps. This determines its true braking strength and confirms its maximum load-bearing capacity. But that's only the beginning. Additional tests simulate real-world stress. The cable is repeatedly bent, twisted, and flexed under varying pressures using cyclic bending rigs. These trials replicate harsh operating environments, from construction cranes to offshore platforms, where cables endure constant motion and fluctuating loads. Advanced monitoring systems scan for even the slightest imperfection. Microscopic cracks, inconsistencies in structure, or variations in uniformity are enough to trigger immediate rejection. There are no second chances at this stage. Only the cables that pass every rigorous test move forward. Once approved, the cable enters the final production phase, coiling. It feeds into an automated winding system where speed and tension are precisely managed by centralized controls and load sensors. This prevents slack loops or uneven layering that could compromise handling during transport. A synchronized turntable rotates steadily while a transverse guide mechanism positions each wrap of cable exactly where it belongs. On high-end production lines, integrated cameras and displacement sensors monitor alignment in real time, instantly correcting any deviation. When winding is complete, hydraulic clamps secure the cable ends. Traceability codes, batch numbers, and manufacturing data are printed directly onto the coil core, ensuring full documentation from factory to field. Each finished coil is then mounted onto heavy-duty steel or engineered wood pallets and sealed in heat-shrink film or protective oil-treated wrapping to guard against moisture during storage and shipping. Automated overhead cranes lift the packaged coils into staging areas, where forklifts transfer them to the logistics zone. From there, they are loaded onto flatbed trucks or specialized transport containers equipped with anti-roll compartments, ready to be delivered to projects around the world. From a rough chunk of iron ore to a precision-engineered steel cable capable of supporting hundreds of tons, every step in this journey reflects advanced engineering, relentless quality control, and industrial power. If you enjoyed this deep dive into modern manufacturing, hit like, drop a comment telling us which stage impressed you the most, and subscribe so you don't miss our next behind-the-scenes exploration of how the world is built.